Okay, so today we'll be talking about chemical kinetics, in which we'll first talk about the empirical laws and mechanism. We know that chemical reaction depends on three things: temperature, pressure, and concentration of the species. Fourthly, it depends also on a thing called catalyst or inhibitor. If a catalyst is present, then the reaction rate will increase, and if an inhibitor is present, then the rate will decrease. And the decrease will take place in the power of 10, not by 1 or 2 factor, but by a higher factor. We know that the reaction changes with time. So what happens? When a reaction starts, the reactant starts decreasing, and the product's concentration start increasing. So these are the two things that changes with time. So our next question becomes that how do we measure the rate? So what we do is, as time goes, we measure the change of any convenient property of the reactant or products which changes with time. What are the properties that we choose? So the conditions for the property that is to be chosen to measure the rate is the first point is it should be reasonably easy to measure, and it should change sufficiently in the course of the reaction to permit an accurate distinction to be made between various composition of the system as time passes. So the property that we will be measuring should be easy for us to measure, and the second is that the property that changes should be large so that we can measure it. Okay, so here's an example of sucrose inversion. How is the rate calculated for this? So whenever a light beam, that is plane polarized light, passes through sucrose, the beam of plane polarized light change. When we know when sucrose inversion takes place, the d alpha dt also changes, and so by measuring the d alpha dt we can track the rate. So methods by which a reaction can be followed with time are: first is changes in pressure, changes in pH, changes in refractive index, changes in absorbance at one or more wavelengths, changes in thermal conductivity, changes in volume, and changes in electrical resistance. Mainly, these are 7 forms in which we can monitor the rate of a reaction, but we can also come up with new ways at any time. As chemical reactions are sensitive to temperature and pressure changes, the reaction should be done in controlled temperature and pressure conditions. This becomes very important when we monitor a reaction. If the temperature and pressure is varied largely, then we cannot monitor the reaction, as the reaction is very sensitive to temperature and pressure changes. This graph shows how product and reactant decreases or increases with time. As we can see, as the reaction goes forward, the product concentration increases and the reactant concentration decreases. So the concentration of reactant will decrease from initial to equilibrium value. This is the equilibrium value. So the product concentration was 0 in the beginning, and at the equilibrium value it has risen up, and in the case of reactant it has decreased from the initial value to the equilibrium value. So writing chemical equation in the general form, we can write it as this, where Ai is the chemical formula of the species, mu I is the stoichiometric coefficient. For reactant, mu I is negative because it decreases with time, and for product, mu I is positive because it increases with time. Now, the number of moles of the ith species, that is the reactant species, or the product species, in whichever we can call that an ith species, is given by the formula this: Ni is equal to Ni0 plus mu I epsilon. Okay. Now, this epsilon is the advancement of the reaction. As we go forward, this epsilon increases or decreases depending on the reactant or the product species, whichever is considered. So Ni0, the number of moles of the ith species initially, is given as this Ni0. So on differentiating this, we get dni dt is equal to mu I into d epsilon dt. We know that the rate of the reaction is the rate of increase of the advancement with time. So this is how a rate of reaction is defined in chemical kinetics terms, the rate of increase of the advancement with time. So d epsilon dt is itself the rate of the reaction, and we know that d epsilon dt is equal to 1 by mu I dni dt, which is what we get later on, and this is again the rate of the reaction. So a rate of reaction can be expressed in this form. Now if we consider a reaction, say 2N2O5, that is nitrogen pentoxide gives decomposes to give 4NO2 and O2. Okay, so the rate of reaction in this case we can write as d epsilon dt is equal to 1 by the negative coefficient that was given in a balanced chemical reaction, that is -2 dN2O5 dt, is equal to 1 by the coefficient that was in front of NO2, and that will be positive because it is a product. So 1 by 4 into dNO2 dt. Similarly with dO2 dt, as the coefficient is 1, in this case it will be 1 by 1. So in words we can say that the rate of the reaction is equal to half the rate of the disappearance of N2O5, or 1/4 the rate of formation of NO2, and equal to the rate of formation of O2. So what do we do now is select some measurable property of the system Z with a known dependence on the mole numbers or concentration of the various substances participating in the reaction. What is Z? Z is any physical or chemical change that we can monitor with time. So it can be any physical property or chemical property that we can monitor with time, so that we know, and if we know the relation between that physical change and the rate of the reaction, then we can monitor the rate of the reaction indirectly. So that is what we do. We know that Z is a function of the number of moles of each species in the system, so we write it as dz dt is equal to dz dn1 into del n1 by del t. Similarly with the second species, and so on. So we know that dn1 dt can be written as mu1 into del epsilon del t. So we replace that in all the expressions, that is del n1 del t is equal to mu1 into del epsilon del t, and we get the following expression. If we continue with that, to get the del epsilon dt, we get the numerator as dz dt by the following expression. This gives us the rate of the reaction. So here we relate this species, the rate of the reaction, with the change in the physical property that we are going to monitor and divide it with this expression to get the rate of the reaction. Okay, now if the volume of the system is kept constant, then we can write 1 by v del epsilon dt, that is equal to the expression that we got before. We know that the units of the rate of the reaction are mole per meter cube or mole per liter, as is required in a problem. Now as an example, we will study the rate of decomposition of acetaldehyde by measuring the pressure in a system at constant volume and temperature. We know that acetaldehyde decomposes to give CH4 and carbon monoxide. At T is equal to 0, acetaldehyde we have N10 moles, and as the reaction hasn't begun yet, so the concentration of methane and carbon monoxide each is equal to 0. At equilibrium, epsilon amount has already reacted, so CH3CHO's epsilon amount will be decreased, and each for methane and carbon monoxide it will increase with the same amount. We know for pressure we write the expression P is equal to nRT by V. From there, using that equation, we can come to this expression where N1, N2, N3 is the total number of moles in the system, right? So P is equal to N1 plus N2 plus N3 into RT by V. We know that N1 is equal to N10 minus epsilon at equilibrium, N2 equal to epsilon, and N3 equal to epsilon. So we add all of them and we get N10 plus epsilon into RT by V, which gives us the expression of the resultant pressure at equilibrium. So initially it was P0 equal to N0 RT into V RT by V, and at equilibrium we have P is equal to N10 RT by V. So we write it here like this: P, if we break this thing in the bracket, N10 into RT by V plus epsilon into RT by V. So this is the initial pressure, so we replace it with P0 here, and so the resultant pressure's expression comes out to be equal to P0 plus epsilon RT by V. Now we differentiate P with respect to T and we get the following expression, that is dP dt is equal to RT by V into d epsilon by dt. Now d epsilon by dt 1 by V into d epsilon by dt, this is the rate of the reaction per unit volume, right? That is equal to 1 by RT dP by dt. So this is our measurable property that we can monitor. This is the physical property that we can monitor, and using this we can find out the rate of the reaction that is required for us to find out. So that brings us to the end of the lecture of the chemical kinetics of this phase. We'll continue with the next phase in the next video.